Welcome. In this session, for the support vector machine, or SVM, we'll explore how to incorporate a kernel function into the dual formulation. Let's remember that we're given m data, and these are vectors in some vector space. And let's suppose that we believe that they could be separated if we embedded them in a higher dimension. And let's suppose that we're also given some kernel function that performs that computation. Instead of doing the embedding and the dot product, the kernel function does the result. So it's a kernel function with two arguments, both in the same dimension as the data are. And then what we can do is we can compute x hat transpose. And this is called the Gram matrix, after the mathematician Gram. And this has entries of the kernel function of data vector I and data vector j, and the Gram matrix is symmetric because the kernel function is symmetric, and because of the other properties of the kernel function, this has to be a symmetric positive definite. Now let's suppose that we're trying to do the we try to compute the SVM. So the original SVM dual formulation was it had the objective was minus 1/2 of the transpose of the Lagrange multipliers times the label matrix times the design matrix times the transpose of the design matrix times y times the Lagrange multipliers. Now, what happens when we embed? So, after embedding, what we get is minus 1/2 alpha transpose. So the labels don't change and the dimensions don't change. X hat becomes an m by n plus k. X hat transpose becomes an n plus k by m. So the product is still m by m. And then we multiply that by the label matrix by the Lagrange multipliers. And this can be written as minus 1/2 of alpha transpose y. This is now the Gram matrix. And so we never actually have to compute the embedding. All we have to do are compute the entries of the Gram matrix. So that would immediately seem to be a quadratic problem, because the size of the Gram matrix for m data is m by m. In the SMO algorithm and interior point methods, only relevant pairs of data vectors are used, and so we only have to compute single entries of the Gram matrix. What are some useful kernels? So these are typical. This is not a comprehensive list. These are kernels that in practice people have found to be useful. The first is the linear kernel, and the linear kernel doesn't change anything about the data. It doesn't actually do the embedding, and its kernel function is the transpose of the first vector times the second vector, and that produces the original XX transpose. The next one that people will often explore is polynomial, and if we let the order be L, then the kernel function will look like this. Will be U transpose V, and then we can add some constant C, and then we can raise that to the power L. The embedding that we came up with by hand was very close to being this. A specific version that people will often try is a quadratic, and the kernel function for a quadratic kernel is we take the dot product of the vectors, add 1, and then square it. And this is closer to what we saw. This will actually lead, I believe, to 6 entries, not 3. So this greatly expands it, but it's still finite. Now, I kept saying that we were embedding into a finite dimensional space. Well, there's a possibility of embedding into an infinite dimensional space, which doesn't make computational sense, but the kernel does. And a commonly used kernel for the support vector machine is the Gaussian. And in this, the kernel function is we take E, and what we do is we take the norm of the difference between U and V, and we square that norm, and we negate that, and we divide it by 2 times the standard deviation. So in this case, the user has to provide a hyperparameter, sigma, which is the standard deviation of the data, and this is basically a bell curve. When U and V are identical, this is e to the minus 1 over 2 sigma squared, which is the smallest, which is the largest possible number. And then as this becomes greater, e to the minus a greater number gets smaller. And what this will do is, if we plot the difference between U and V, and we square that, so it's got to be 0, this will produce a Gaussian. So it'll be 1/2 of a bell curve. And this kernel is really powerful when it comes to performing the support vector machine. What it will do basically is it will construct a little Gaussian around every support vector. We'll go into that in a subsequent session. The MATLAB standard is with standardized data, and when the data have 0 mean and unit length, so standardized unit variance, standardized data, for that the kernel function is e to the minus of the norm. That is, this has been taken care of in the standardization process. And this is the, if we call MATLAB and we let it standardize the data for us, which it will do in the support vector machine, then this is the computation that it will have. There are others. There are Laplace is a variation on it where we don't square the data and we normalize it in a slightly different way. Generally speaking, the linear, quadratic, and Gaussian are for moderately complex data 3 of the kernel functions that we'll first try to see whether we can classify them. What have we explored in this lecture? Well, we've explored data vectors that are not linearly separable, and we consider embedding these data vectors into a higher dimensional space. We can compute the dot products in this higher dimensional space using a kernel function. These compute the dot products of the embedded vectors without actually going through the embedding. And the Gram matrix is a matrix for the design matrix. It's the same size, it's a square matrix, that has the same number of rows and columns as there are data entries, and it's a symmetric positive semi-definite matrix that represents the kernel function applied to each pair of data vectors. The kernel trick is using the Gram matrix in the dual formulation.